Let's talk about the dream of augmented reality. The one where all its incredible power, 3D objects, useful info, you name it, is somehow packed into a pair of glasses you'd actually want to wear. For decades, that's been pure science fiction. Well, today, we're going to break down exactly how it's becoming science fact.
And look, this isn't just some far-off concept. This quote comes from the folks behind a real project called Orion. And to pull this off, they had to invent breakthrough solutions for pretty much every corner of modern computing. We're talking about solving some of the toughest engineering problems out there, all to fit a whole new reality right on your face.
So, to make that dream feel real, to make it genuinely immersive, there was one piece of technology the engineers had to get absolutely 100% perfect. It's called world-locked rendering. Okay, so what is world-locked? It means that if you place a virtual object, say a coffee cup, on your real desk, it has to stay put. It has to feel like it has real weight and a real place in the world. If you walk around it, it can't drift, it can't jitter, it can't lag. The second it does, the illusion is completely shattered. Even worse, it can actually make you feel sick. So perfect world-locked rendering isn't just a feature, it's the absolute foundation of believable AR. And achieving that perfect lock is, well, it's a marathon. The glasses have to perform this relentless, non-stop pipeline of tasks. First, track your head's exact position. Then, capture the 3D layout of the room. Then, render the virtual objects from that perspective. And finally, blend it all together with your view of the real world. This isn't something that happens once in a while. It's happening constantly, every single moment you're wearing them.
But here's the catch. Trying to squeeze that continuous pipeline into a tiny, lightweight pair of glasses runs you headfirst into two of the biggest villains in all of computing. First up, we've got latency. This is the emotion-to-photon lag, that tiny, tiny delay between you moving your head and the image in front of your eyes updating. Even a few milliseconds of lag is enough to make a virtual object feel disconnected and floaty, totally ruining the illusion. Then you've got its partner in crime, power. All that processing creates heat, and, of course, absolutely drains the battery. Nobody wants to wear glasses that get uncomfortably warm or just die after 30 minutes.
And this really gets to the core of the issue. See, a traditional computer, like your phone or your laptop, works in sprints. You tap an icon, it works really hard for a second, and then it goes idle to save power. But AR glasses, they can't do that. That world-locking pipeline is a continuous, never-ending workload. A traditional chip is a sprinter. AR needs an ultra-marathoner. And that changes everything. So it became crystal clear you couldn't just take a massive, power-guzzling chip and shrink it down. It just wouldn't work. The Orion team had to come up with a totally different approach, a distributed one. Right, so instead of one jack-of-all-trades chip trying to do everything poorly, they designed a team of specialists. Think about it like a surgical team, right? You don't have one person doing the surgery, the anesthesia, and the nursing. No way. You have a team of experts, each one perfectly optimized for their specific job. And that is exactly how they designed the silicon. So let's meet this all-star team. The entire solution is built around 3 custom-designed processors, all built on an advanced 5-nanometer process, and each one has a very specific mission. Here they are. First, the glasses processor. That's the sensory hub. Then you've got the display processor, the finishing artist. And finally, the compute coprocessor, the heavy-lifting genius of the group. And just look at those different transistor counts. That alone gives you a huge clue about how specialized and complex each of these chips really is. Okay, first up is the glasses processor. You can think of this as the device's central nervous system. Its whole job is to see and hear the world around it. And it does that job with a mind-boggling 2.4 billion transistors. So yeah, this is no simple controller. It's a powerhouse of perception. Its mission is to wrangle this absolute fire hose of incoming data. We're talking inputs from 7 different cameras. It has specialized hardware to speed up eye and hand tracking. It handles all the audio coming in and going out. It even compresses all that data so it can be moved around efficiently. It's the ultimate input/output manager. Next in line is the display processor. This is the finishing artist, and it has one single critical job: make the image perfect right before it hits your eye. Now, it's the smallest of the 3 with 1.1 billion transistors, but don't let that fool you. This little chip is the final line of defense against lag and any kind of visual imperfection.
So this processor's star player is something called a reprojection engine. It's a brilliant trick that makes last millisecond adjustments to the image based on your very latest head movement. This absolutely slashes that motion to photon lag. It also does final color corrections and is physically baked right into the display module itself for maximum speed. And that brings us to the heavyweight champion of the team, the compute coprocessor. This is the brain of the operation, the one that does all the really complex thinking. And it is an absolute beast. Get this, 5.7 billion transistors, all dedicated to the most demanding, brain-melting AR tasks. This chip is where the real magic of understanding the world happens. It's running the complex computer vision algorithms to map your room in 3D. It's powering the machine learning engine for smart interactions. It even renders spatialized 3D audio, so sounds seem like they're coming from the right place in the room. This thing is the powerhouse. So, when you pull all of this together, you realize it's way more than just a clever fix for one device. What we're really looking at is a blueprint for the entire future of wearable computing. I mean, look at what this specialist distributed architecture achieves. You get the ultra-low latency you need for a totally seamless experience. You get the aggressive power management you need to actually wear it all day. And by breaking up the work, you get a system that's more efficient, more secure, and even easier to upgrade in the future. It solves the core problems. And really, that's the big takeaway here. For so long, the incredible dream of AR has been held back by the hard physics of latency, power, and size. This specialist approach, this team of experts on a chip, finally gives us a path through those barriers. And that leaves us with the most exciting question of all. Now that the how is finally being solved, what amazing worlds are we going to choose to build?